Change of the resistance, but after a few minutes or so, we are back at this 0.15%, which is the AMR. And if you go back to the slide where I showed you the domain structure, you could see that after the application of a field, we still had a lot of domain walls. So the interpretation here is that here, directly after applying the field, we have no more domain walls. We have a fully aligned state. And then later here, we have the formation of domain walls, so that you actually have a domain wall meter resistance that gives you this 0.75%, and the pure AMR is the 0.15%. So this is something that we're still working on. I think it's quite interesting because it allows you to read out the state of metallic antiferromagnets. Then just a few words on layered antiferromagnets is something which you recently started to work on, which I think is very exciting. There's lots of literature out there. And for instance, these trihalides, such as the chromium chloride, is a very exciting material because it's a layered antiferromagnet, which for one layer is a pure ferromagnet. It's a pure antiferromagnet because you are fully compensated. And then for 3 layers, it's again, you have one layer which is in that moment. So you can make this, you can switch between ferromagnet and antiferromagnet by changing the number of layers. We recently went to a more complex antiferromagnet, this chromium thiophosphate, and we measured some angular magnetic resistance response, which is something we're investigating at the moment to try and find out where this comes from and if we can thereby also read out the state of these 2D antiferromagnets. So to sum this up, so the electrical readout is possible in insulators using spin-Hall magnetic resistance, in metals using anisotropic magnetic resistance and domain wall magnetic resistance. And for imaging, we can get readout by X-ray magnetic linear dichroism as a contrast mechanism. But there are also other mechanisms that I didn't introduce today, but that are quite important, such as the thermal spin-Seebeck imaging, anomalous Nernst effect, imaging uncompensated moment, second harmonic generation, magneto-optical Kerr effect, exchange bias, and so on. So there are a lot of ways to read out antiferromagnets, but it's important that we can do that electrically. So now let's get to the writing. Now, let's first start with fields. I already showed you that the susceptibility of antiferromagnes is small. That means if we apply a field, we get a canting of the two sublattices, which is very modest. So we have a canting of a few millirad or something like that. However, what we can achieve is that if we orient the field in a different direction, the two sublattices will actually also rotate to actually align themselves perpendicular to the applied field. And that is so-called spin flop. And then we have the net moment due to the canting, which is parallel to the field, reducing the Zeeman energy. And in a very rare case where you have not very strong exchange coupling, but strong anisotropy, you might even get a spin flip, but we're not going to consider that. I just say that for completeness. Okay, so let's see if that really works, the spin flop. So actually here again is the example of our antiferromagnet. When if I apply a strong field, then we see that the sublattices orient perpendicular to the field. And if they are already perpendicular to the field, then they just cant a little bit in applied field. And we measured the extramagnetic linear dichroism process. So you see here the canting of the sublattices with the applied field. And so what we did is we measured the extramagnetic linear dichroism spectra for a sample which we oriented by a strong field. So it's mostly monodomain pointing in the see that we have the spectrum where we get first a dip and then a peak. And then if we rotate the field by 90 degrees, we first get a peak and then a dip, rotated the Néel vector due to this applied field. But usually that takes a lot of field to do. So like in this case, maybe 60 Tesla. And that's difficult to implement in a CMOS device. Now, an alternative approach is to actually use strain. So strain can also induce anisotropies, and therefore by applying a strain, we can orient the Néel vector in a direction set by the anisotropy due to magnetoelastic coupling, which many of these antiferromagnets have. So this is the strain gauge, which looks a little bit like a medieval torture instrument. We can put the sample on it, torture it a bit, and then do it until it breaks. And